Okay, guys, I'm starting the stream a bit later because I had to do some stuff in the morning, but we're going to go 4 hours this stream until 4:25 roughly p.m. Central European time. Let me share the link with the Discord people. Here's the link. And here is the Discord. And by the way, let me show you the latest logo we have, or better said, banner. We'll be going through 2 papers. Let me just tell people what we're gonna do. So there are 2 papers that I want to read through that will be useful. I hate these links. Let me maybe paste it just from the video description itself. So here are the papers. Okay. How are you guys doing? Let me turn on the live chat. And let me show you the new banner we have. Look at this, guys. Open NLLB, no language left behind, but open source checkpoints for unrestricted commercial use. I'm going to grab this one. I want to download this image. Let me just see, how does one do that inside of Discord? View, edit, pin, reply, create. Where is the, can't I just like download this or something? Copy the image, save the image. Will it save it locally or? Okay, nice. Nice. Let's go to, let's make it open NLLB banner. Let me save it to downloads. Actually, ideally, we would save it directly into the project. So let's maybe go, let's go home, let's go projects, let's go NLLB, let's go to, I guess fairseq, and then save it here. Okay, now that I've done that, let me go here. Let's grab this name and let's update our README. So in the README, we want to have this one. Let me see what's the resolution, by the way, before we break something here. What's the size of this one versus the one we just uploaded? So this one is 31 kilobytes. What's the resolution? Do you see it? Because I don't. Come on, it's just one piece of information that you need about the image when you open up settings, like properties. I just want to know what's the size and what's the resolution. And then where is the latest one? I just pasted in. Open NLLB banner. Okay, this one is a bit bigger. 3.7 megabytes. And the resolution, no idea. Let me just open it up here. Can you send a smaller resolution? Or I can just try. I'm not that good in Ubuntu, so I'm struggling a bit with. Let me see the properties here. So yeah, it says this is too big. We don't need that big of an image. We can go 2x smaller at least. Let me see what's this official one. The official one is, so this would be perfect resolution. 120, 1280 and 640. Sarah is basically taking care of this design. She proposed this banner and people just loved it. So we went with it, and then we can always evolve it. But the reason we have Ara is basically because these birds are obviously very good at mimicking human language. Also, language models are oftentimes referred to as stochastic parrots. And then finally, there is the robotic aspect of it. So I think it's very, very symbolic and a good fit for the project. Personally, and people did love when we proposed our a couple of days ago. So, having said that, waiting for the upload of the new image. Please send it here. Otherwise, I don't want to open up personal DMs on the stream. Okay. Let's grab the image. Thank you. And let's save it again. Open NLLB. Go to projects, NLLB, fairseq, and just save it here. Let's go. Much better. And let's see what the, okay, it looks the same. Just a second to see the size is 1 megabyte. Okay, that's more that's better, but still, why is it so big compared to the, I guess this one is not as compressible as the one that we have here. Maybe let's convert it to JPEG. Can we convert this to JPEG? Just save as. How does one convert this in? Sarah, can you maybe send a JPEG version? 1 megabyte is too much for this image. This can be nicely compressed using JPEG. That's my digital image processing background speaking for me. Converting image to JPEG in Ubuntu. Let me see what people say here. How does one do that? Try these commands. Format PNG into JPEG using Mogrify in the same directory. Okay, but like, now let me see whether I have this tool. Where is, whoops, where is Mogrify? Do I have it? Probably not. Let me just try and run it like this. Not found, can be installed. Okay, what else do we have? Move. Why is everybody suggesting generic Linux? Image magic. Okay, let's see. Do I have that one? Let's just try and install it. Okay, apparently I didn't have it. We'll need it either way. Maybe if Sarah converts it quicker than I. Just need to know the maximum size you can do. I mean, as a reference, the image that we currently have is 31 kilobytes. And this one is 1 megabyte still. But like anything around 100 kilobytes is acceptable. Let's just see. Get some PNG images, blah, blah, blah. There are too many ways to convert. Blah, blah, blah. Install, and then how do we do it? Using to convert. Okay, once the image is open, follow the instructions. Go there. Aha, so Mogrify will format. Okay, Sarah sent it already. Okay, that's amazing. Third attempt. Open NLLB JPEG. Again, let's go to the project. And let's save it here. Let me just delete the previous ones. So we don't need this one. We don't need this one. We just need the JPEG version. We can delete these. And now let me copy this. Let me open up README. And let's just do it like this. I'm not sure what this raw will do. I usually never put raw. But let's just keep it as it is. Whoops, not that. I want to just preview. Looking nice, guys. And what does this text do? Is this just... Okay, I don't see anything changing. Let's commit this. Let me just copy a path here. Copy path. Change directory there. Okay. Let's see what we have here. So, for now I just want to add README, and I want to add the image. Did we paste the name correctly? I think we did. Looking good. I don't want anything else here. Custom eval, temporary, we'll check in all of that a bit later. All of these are just YAML files, calculate metrics, download parallel corpora. We've changed quite a lot of things, but in this push, I just want to do this. So commit, update the banner image in the README, in the main README, and let's push this to the origin. Let me just do this. Okay. Cool. Nice. Let's see the updated README. Did it work? And open up this. And here we are, guys. Nice. Nice, 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 nice. Looking good. And there is the getting started document here. So we're gonna we'll slowly be working and merging this project into, shaping this project into something that we want. Okay. That was the first task. The second one, I want to understand sharding in fairseq. Let me just close up all of these windows. Let's go back to here. So last night I tried to introduce some model sharding into our training. So as opposed to using data parallelism, let's try and use model sharding or parameter sharding, which is the FSDP equivalent of Megatron's model sharding. So whatever works, I'm just trying to find any solution really at this point. Let me see what they say here. So Megatron 11B is a unidirectional language model based on Megatron LM. Following the original work, we trained the model using intra-layer model parallelism. Okay, trained the same data and uses the same BP as Roberta. Here is the model. Here's the architecture, training details, batch size 512, number of updates 300,000, peak learning rate, inverse square root. Okay. Contains too many parameters to train a single GPU. Okay. Using the vocab parallel cross entropy criterion, we similarly split the loss computation. Okay. The following training command illustrates how to do model parallel training in fairseq. Okay, model parallel size. I think that's what I tried last night. So we tried to just set long JSON to what's the name? The name is model parallel size, and as you can see here, I've set it to 2, but it didn't work. Something was crashing. Now we're gonna get to the bottom of it. You may combine this with data parallel training by increasing distributed world size. Okay, so I think I'm not sure whether this should be set to 1 or 2. I tried 1, then it failed. So I set it to 2, and then it was failing on some different part of the code base. So tested on DGX. Okay, results. Evaluating. Download, detokenize, BP. We don't care about any of that. Evaluating. renormalizing, perplexity. Okay, we don't care about anything there. What I care about is, additionally, do they have any mention of, let me see, do they have any mention of parameter sharding? Let me see. Just a second. Flores. I think we can close this down for now. Just a second, guys. Okay, let's just try. I know they have pipeline parallelism. Is there parameter sharding in fairseq? So that's the FSTP. We probably have to check it in fair-scale, by the way. How can I parallelize generation of a sharded dataset? No, we don't care about dataset per se. What we care about is this. Is there any mention of sharding? Sharding full enables full sharding. CPU offload. Okay. Via the following arguments. I think this, we might be limited, guys. We might be limited in what we can do, which might suck. By fully sharding the parameters. Okay. Yes, I'm gonna show you as soon as we start reading the paper. You're gonna see that after we are done with this. I want to first finish going through this sharding, understanding the sharding, then we can go and figure out stuff about interpretability and hallucinations. We have 2 papers coming up. 13 billion parameters with CPU offloading. Okay. Checkpoint activations. Maybe we can try this one. We can experiment with this one a bit. Let me just put a to-do here. I don't want to mess up. Let me just close this. I don't want to mess up my old config, so I'm just adding to-dos. Checkpoint, try this, see how it affects our peak mem. Okay, let's go, guys. That's one thing. Requirements: install the latest master version of, oh snap my life, this might not be supported on the branch that we are in. You'll need 32 gigabytes of GPU memory. Let me just see one thing, guys. If we go to the project, what's currently in the installation? Fair-scale, clone, checkout experts LT. We might not need this. We might not need this. So fair-scale is likely currently, if we go here, fair-scale, git log. So we are on that particular branch, which is what? Git log, which happened 2022 May. So we are very much behind that code, the latest code in fair-scale. Okay. 32 gigabytes of GPU and 256 system memory. If you have less, okay. CPU offload, max update. So what do they have here? fairseq train, location of the data, FP16. They have CPU offload, which we don't want to do. It's going to slow down things too much. Token, and I don't have enough system memory. I have 64 gigabytes. Or maybe for smaller checkpoints we won't have any issues, but language modeling, tokens, batch. Let me just see whether anything interesting in here. Warm up, max update. Okay. Without offloading. Okay. However, without offloading, we'd only be able to fit a batch of size 1. So what do they do here? Backend, CPU offloading. Okay, architecture, learning rate, total number of updates. Okay, so that's everything there. Let's go here. There was some solution here. Okay, I've seen this last night. Let me go to fairseq, sharding. Parameter or model sharding. See parameter sharding. Okay. Let's see the close issues. How to use customized backward hook. Does FSTP support? Reshard. Issue with auto wrapping. Expert sharding. Let me see what they say there. Model sharding. Okay, let's start. And let's see also, so that's parameter sharding. Let's see model sharding. Is there anything interesting there? Something new that happens? Can exclude layers, model uploading issue. Okay, nothing fun there. How to use customized VRAM limits, consumes the same amount of memory. Some questions. Could FSTP work with mixture of experts? Offload without checkpointing. Support 0 offload. Okay. Let's maybe try from this one. Propose a model sharding plus optimizer set. Okay. Motivation. Use pipe Megatron. Okay. Done by the team in 2021. Do they have any pull requests associated with this one or what? Close is completed because mention this issue here. Maybe here. Why is this not clear in their documentation anywhere? Check the initialization function. It takes 2 process groups optionally. Okay. Zero sharding. I don't see anything smart here. Getting started. Has been upstreamed. I've seen this plug, that's why I'm here. Model sharding using pipeline parallelism. Okay, this looks like what we're looking for. Okay, let's kind of read through this because I don't see any other option. What I'd love to do is just, yeah, ideally just specify the model sharding degree and get the whole thing working. I know that might be too much to ask for. While we're doing that, let's try this one, guys. Checkpoint activations. Let's see what will happen if we remove this for a second and set this to 2. Let me see whether I messed up anything here. To do. Revert them back to 12 layers. Okay, let's revert it back to 12 layers quickly. And then, okay, I've done that. This is fine. Checkpoint activations. Let's try this, guys. What will happen if I do this? Okay. Just quickly run the train. Train.py. Run it and see what happens with my SMI. What's the SMI output here? Okay. I want to see whether we are hitting peak of the VRAM on both. So again, both GPUs, I have 24 GB per GPU. Let's see how this is gonna work now. I'm gonna put it on the second screen. I already see it's loading the model. Okay, 5, 6 gigabytes. Let me show you here. Okay, 19. Will we go above 20? Will we go about 20 with? It's a bit slower, by the way. I hope it's not too glitchy on your side. But it seems we're training. And we did manage to shave off something off of this one. But here we still have 22 gigabytes, 23 almost. Okay. Let me move this. Let me see what's going on. It's still not training. 20 and 23. Let me wait for it to load it. Okay. Let me remove all of the breakpoints and just hit F5. Hit F5 on both of them. 2 processes because of 2 GPUs. And now it's training. It's training. It seems as if one of these is now working a bit better. So before we had 23 GB on the 0th GPU. Now we only have it on the second one. Let me see. I'll have to quickly change a setting actually here. Let me go back to the long JSON. We need to set the intervals here to a bit higher than 100 to like 1000. Same here for validate. Because otherwise we're running the eval too often, and then that might be messing up the memory footprint. So let's rerun it, and let me just put this on the side here. Something like this. So we are preserving the GPU VRAM usage there while we're waiting for the training to start. Okay, loading. Here we are. Okay, we are around 19 here. Let's see. Still waiting for the training to start. I think it's already running. I can hear the GPU actually whispering in the background. Let's see. Waiting for the output here. 20 GB, 23. It definitely seems like it's much slower. Okay, epoch 1 update. Number of updates 100. Let's wait for the second one. There is a big slowdown. I can already notice there is a big slowdown because of checkpointing. So basically during the backward pass, we have to recompute all of the activations. Thus we are saving the memory footprint, the peak, but we are messing up the speed. Let's wait for yet another update here, and then we're gonna make some conclusions whether we managed to save the peak memory. Either way, we'll have to get much more compute, but even when we have more compute, how are we going to distribute across if we don't understand how fairseq or fairscale, what it enables us? So we have to know how to shard the model here. So okay, it seems this is the peak. I'm gonna stop the program now, and let's test the same thing. I'm just gonna comment out a single flag. So again, long JSON, I'm gonna comment out this single flag. I'm gonna kick off the run again. This might slow down things a bit on your side. My stream might be glitching a bit. So you can see we start from the baseline of 2.4. That's for OBS. OBS and the streaming to YouTube is currently taking some GPU capacity. Let's see once the model starts training. So you can see now it's loading. We're loading the data. Onto the GPU. Let's see 18. So we were at 19 before when we were training. Let's wait a bit more. This should now explode to like 23 once we start doing forward and backward pass. So there are no activations yet. That's why this is so low. So this one is already over 23. Let's see for the second one. By the way, all of this unfortunately can be misleading because sometimes this just shows us the reserved memory. I'm not sure how much of that is actually needed by the... Okay, we can see it's actually running already. We're just maybe 1 GB more. And here as well a bit more, but nothing significant, right? And we are much faster. So I'd have to dig into what's going on in the background when we do checkpoint activation checkpointing. Maybe there is some bug as well. But roughly, let me think, 1 GB, how much of activations are we expecting? If it's like FP16, even if we stored activations for every parameter, two bytes per parameter, that's 1 GB or something. So I think this is reasonable. Okay, I'm gonna stop the training now. Let me just reproduce. Let's make sure there was no random variation due to whatever. Let me just rerun it once more. Let's make sure we observe roughly 1 GB less per GPU. Let's go. Okay, 4.8 and climbing up. Okay, 17, 22. Let's wait for the training to start. So now this is with activation checkpointing. This was 23.6. This is also lower. There definitely seems to be something going on there. Let's wait for the first output here, but again, notably lower number of updates. Okay, definitely lower footprint. Let's try commenting it out once more. Rerunning train. Let's rerun this. Confirm that one is now above the previous peak. And then we can go and see what else can we do. We can maybe try CPU offloading. I'm not sure what's going to happen with my system memory. How much memory do I have here left? So my RAM currently around 20 GB, 23, 24. If we start offloading, we can test that just to see how it works. 24.7 currently. Okay, this is now higher again, 23.6, but this one is lower than usually. There seems to be some very random variation, and for some reason this one always has more. higher peak, which is not intuitive because this one is also running OBS streaming. Okay, now it's rising up a bit. Not a clear gain. I'm not super convinced. This one is kind of consistent, but this one was going back and forth. Okay, let's stop it. Let's try the CPU offloading. Let me try the CPU offloading. So, oops, not that, but instead let's go here. CPU offloading, or just offload. Trainer. Offload parameters to CPU. So we can be memory efficient. Apparently, even if we set offload, unless this is false, we won't have offload. Okay. Reshard after forward. Mix precision. Reduce scatter, flatten. Compute type. Bucket. Cap. What's the bucket cap? Let's see this one. Bucket size 25 by default. Is that megabytes? Yes, 25 megabytes. Okay. Okay, let's try one thing. Let's go to learn.json. Let's go to memory efficient. And let's remove it. Okay, so we don't have checkpoint activations, and we don't have memory efficient. Let's now see what's gonna be the footprint. So this is 12, that's good. Return back memory efficient, we will. This is good as well. We commented this out. I think that's mostly it. Any other to-dos? Yes, this is commented out. All looks good. And now we have to first run this just to see what's going on, and then we can do the offloading to CPU. Okay, let's kick this off and let's track the behavior here. Let's see how much of memory this memory efficient helps. Will we hit CUDA out of memory now or not? We might. Let's see. Are we using FP16? I think we are. Okay, it's gonna start now. Let's see. Okay, this one is already 23. The other one is 23 as well. Oscillating back and forth, 23. 24. The one below is 24. Let's wait for it to start. 24 down below, that's definitely higher. And the bottom above is also oscillating between 24 and 17, 23. Why is it jumping up and back? My god, shouldn't it be stable? Just allocate the damn thing and don't move. What is this? Okay. It seems it's running. 22, 20, 23, 21, 22, 13. What? Why are you jumping back and forth? Okay. Notably slower. Training. Notably slower training. And it seems it's also higher footprint, but not clear how much. This is just going back and forth. Super slow training. Okay, not super slow. We already have some outputs. But this is going back and forth from 15, 13 to 24. Okay, let's stop it. Let's now add offload CPU or CPU offload. So if we add this, let's see what's gonna happen. Launch JSON. Okay, let's go and let's add CPU offload with a dash here. And now let's finally run. Let's see what's going to happen with CPU offload. Now we also want to track the system monitor. Let me see what's going to happen with the with my RAM down below. Tracking at the RAM. 22. Will it even work? That's the ultimate question. Who knows? 26.5. 29. Let's see. Of course you failed. Tensors must be CUDA and dense. What? What else are they than CUDA and dense? Wait. What else are we than CUDA and dense, man? Join. Wait. I think I know where I've seen this line. This is just still dummy initialization. In no reduce. Line 28. Clip gradient norm. Let me just copy paste this so we can analyze it properly. Let me create a temporary file here. We can now stop this. Let me just quickly paste it somewhere. I love creating these temporary files all around the place. Okay. So process one terminated with the following error. Trace back. File. Line 51 in rep. function line 3345 in distributor main train line 216 train step context lib in inner. Okay, train.py line 339 train step line 79 trainer line 1147 in train step raise grad norm trainer let's see, something to do with gradient norm there. Okay, utils again, clip gradient norm all reduced. Interesting. Let's search for this line. So this is in the distributed package in Torch. But it all started from fairseq line 423, this one. Let's rerun. Let's rerun this. Understand what's going on. Why are we hitting not CUDA? Why? It sucks whenever you start using something, you have to go into the source code to debug stuff. I mean, it's a research code base, so who am I to complain? Let's wait until we hit that line. Okay, here we are. If it's initialized, then we enter, and there is this split norm, which is device type, sorry, data type, and then device CPU. Why are you on the CPU? Oh, okay, so you're on the CPU because we've done the offload to the CPU. I assume that's why, but let's see. So we're in the train step. We've done the all reduce. Where is the model? The model should be, where's the sample? Sample, let's see where the sample is. Sample is on device, should be on GPU. Okay, let's grab the net input. Let's then grab the source tokens, and let's see the device CUDA. Okay, that's CUDA, but for some reason, okay, the clip norm. here we enter, and then we enter here, and then we enter here, and then we enter. So what's the self parameters? Self params are generator object. If we grab the first one, I can't subscribe. Okay. And then here, clip gradient norm. Params are what? Okay, and then device, CPU. And then it asks me what's the device? Multi-tensor L2 norm available. Total norm. Expert grads, sharded grads. And then D type. Okay, so we're gonna fail here, right? No, so he's gonna be the tensor must be CUDA and dense. Okay, it's not clear what's going on there. What did fail? Let me quickly see there. Let me quickly see the where is the Megatron? Megatron. Model sharding, fair fail. It had some example, come on. Okay. Let's see what arguments they use to run. Distributed, memory efficient, no mention of CPU. CPU upload. Wing activation to CPU does not reduce the memory. Okay, this will apparently not work really perfectly. Model offloading issues. Okay. Oh my god, nothing. Half of these issues are just hanging. That's why I was looking into GPT UX, because down the lines things like this just turn out to be very painful. Please start with the hallucinations examples, eagerly waiting. Yeah, I will, man, but we have to wrap up this. This is very important. I can't context switch. Then sharding the optimizer state is merely a matter of wrapping your optimizer in fair scale optimization OSS. DDP can be used in place. Fast scale can be sharded using the FSDP API. Involves wrapping your model similar to the API above. Model. Okay. What's this dummy process? Hi, Abchit. There is no mention of anything. There's no mention of how CPU offload should be used. Okay, this is just a bunch of debug stuff. Nothing useful here. Completely not useful. So if this is false, then wrapped model goes to the CPU. Wrapped model goes to the GPU. That's how it's used there. And that's all. That's all of the mentions I see here. Does this even work? Huh. Trouble in paradise. Let me see how did they train the model here? Did they use pipeline parallelism? Nope. Mining pipeline, downstream pipeline. Filtering pipeline. Okay, is there any mention of parallelism? GPU. Okay. 80 gigabytes of VRAM. Okay, let's quickly see. I think they have some commands here. Wait, they have some commands how they train the mixture of experts model. Here's the modeling. Dense mixture of experts is here. Output expert count. Okay, so they set MOE and MOE frequency. Let's see what else. Okay. So some of these parameters must achieve it. So expert count and MOE. Let's try and see what this does. Does this automatically trigger some type of sharding? And also, let me quickly see, is sharding even mentioned in this paper? Sharding. Or distributed. Okay. World. Like world size, overworld. Different parts of the world. World Health Organization. Toxicity, worldview. Free speech. We've seen that. many parts of the world. Nothing useful. Okay, so let's see. We are left with understanding how these parameters are used. Fairseq root output. No, I don't know what all of these do. What I don't know is what expert count does and what MOE does. So let's see these two. What does this do? MOE. Let's maybe just include only the 5 files. And let's see what this one does. So MOE. Local drop. If MOE is specified. Aha, so here might be an interesting chunk of code. Let's see just whether there is anything else that's interesting here. Not really. Where is MOE called? Generate, sweep, test, generate. Top one gate. MOE layer. Expert count. World size. Transformer layer. Okay, there is a ton of things going on. MOE label smoothed NLL loss. Okay, all of this is custom made. Okay, let's go back to the MOE. There was this somewhere we had args MOE or arg. So in this case, you specify a bunch of parameters: second expert policy, normalize, count, frequency. Okay, not really useful actually. Generate multi, we don't care about that. Laser, tabulate, we don't care. This is just a sweep. Expert count. Criterion. What's this MOE layer? As described in G shard. Oh my god. Get the world size. Okay. How can I force it? If we do data distributed, FSTP should shard the parameters, but it's not doing that for some reason. Because I'm seeing a very huge memory footprint. Let's try one small more model parallel size, and then I'm gonna put an issue or something. Like this is not clear at all. Size. So let's put this to 2. Let me see whether I messed up anything. So I wanna comment on this. We don't need that. Revert to 1000. I did. This is 2. Okay. Return back the memory efficient. Okay, maybe we can later do that. Let's try and run this. Does it fail? If it fails, where? It does fail, of course, because it gets the unexpected replication. Okay, an unexpected. Why can't I never get the actual description to the exact path? Spawn, train. Where is this happening? Okay. Line 3 to 326 in checkpoint utils. Line 326. Load checkpoint. And this one is, I think, called in the main function. So if we go to train.py, this one is called here inside of the main. So we will enter this. We will enter this, and that means we will eventually go here. And this trainer apparently doesn't have. The trainer doesn't have that argument because they changed the API. They use the Megatron trainer. So this one its load checkpoint doesn't have this particular. Okay. So what if we just commented out this? What if we just do this? And then we say run again. What will fail now, if anything? Let's see. So again, we're running. We're trying to enable model parallelism. In fairseq. Let's see. Let's run. So far, so good. It seems it's starting. Okay. Did we just manage to do it? And if we did, why the heck does a 615 million parameter model take 40 gigabytes of VRAM? In which world is that correct? Something is just terribly broken here. let me stop this. Stop, and then go to launch.json. And then go to distributed world size. This one should specify, I think, let's just specify 1 here. And let's run. Train.py again. Hit run. Will this fail? Of course it will. Of course it will. Please make sure to call init process group. Well, let's call it. Where is it called? It's called here. It's called here. Initialize distributed. Okay, let's just see what we're doing. We have to unfortunately just step through this because train.py, let's run it. And let's see why is all of this so broken. So distributed init method is none. If it's none, enter here. Let's see what happens in the initialization here. Are you model Perl? I'm not. And then pipeline Perl init, infer slurm, else if all of these are there. Otherwise, force distributed. Let's see what force distributed does. What is this parameter? How does one force this? Well, let's put it to true. Let's see what happens now. Then we will call this single node init. And here it's gonna skip this. Okay, let's go. Run train again. Oh my god, I'm changing a ton of code. I don't like this. Let's see what happens now. Oh my, it's working. I am a wizard. But of course, it's just running on a single GPU. Oh my god. Yeah, but not yet. It's not what I want to do, man. I just want to run on 2 GPUs and shard it. I want to shard the parameters. But if we go and do it like this, then yeah, I'm just gonna submit a issue here. Let me see once more. Is there anything I can pass without having to change the code? Let me just add, I'm gonna create an issue on fairseq if we don't figure it out. Submit an issue, fairseq, asking for model param sharding in fairseq, which uses fairseq. So let me go do one thing. We stop this. Actually, let me go to fairseq again. Fairseq. Temporary, custom, temporary, that does not matter. Did I change anything other than checkpoint? Yeah, I think the only difference is checkpoint utils. That's my only modification. Let's see how this pipeline parallelism works, how much slower it is. Pipeline parallel. Pipeline model parallel. Let's see that one. Let's see pipeline checkpoint. Micro batch count for pipeline. If we just set this, what will happen? Without having to go into too much details for now. If we just go and set, instead of model parallelism, if we just set pipeline model parallel, does it even accept arguments? Or is it just a boolean? It's just a boolean. Okay, so how will they know? How will they know how to split this up? Let's try it. Why are you complaining? Because apparently arguments are not correctly specified. Long JSON. Why? If I comment out this, will it work? Oh, okay, I saw it. I didn't specify the dashes. Okay, run. Let's see what happens. Let's just run it YOLO. Currently required. Okay. So let's go specify pipeline balance. Pipeline balance. Partition them all into NK pieces where each piece contains NI layers. Okay, so how should we specify this? Can we just put like blob 2? Twelve layers. Why don't you explain what K means, guys? A list of device indices indicating which device to place. I have no idea how this is used. For everything, we have to go into the source code and understand how it works. Return a list and the map. Balance. NK pieces, where each piece contains NI layers. Will this work? How should the list be specified? Like, oh my god, guys, if you write code, never do it like this. Like, just put a simple example. If you just told me, hey, 0, 1, 3, I would already know what it is. Come on, it's just like one word. This is my assumption. And then here, I don't know what to put here, like maybe 12, 12. So I'm trying to enable pipeline parallelism currently to run the model, but I'm not sure how to specify the arguments here because they, let me see in the documentation. Do they have pipeline scale? Let's just go to documentation here. Pipeline balance. The sum should be equal to the total number of layers. Yeah, but how do I specify it? Like, what's the format? Can you just tell me the format? Okay. Let's just run it and see where it fails, and then we're gonna fix from there. Okay, so if it's an instance of a string, if we ran eval of 12, 12, will it fail? Just returns back this. And what if we put a comma? Okay, then it returns back this. Okay. So let's do it like this. Train, run. So again, we're trying to get the code running with pipeline parallelism because I have two GPUs, and I'm just trying to pipe them so that the first 12 layers from the encoder are on one GPU, and the second 12 layers from the decoder are on the second GPU. And again, it failed here somewhere, and it didn't even tell me where. This code is just so broken. As soon as you start going a little bit outside of what it's designed for, everything is not working. Like, expected all tensors to be on the same device, but found at least two, CUDA 0 and a CPU. Oh my god. Oh my god. Let me just see whether I messed up. Maybe I have a CPU offload flag turned on, but I doubt it. CPU, no. To do revert, this is fine. This is set to 2. Return back to memory efficient. 12 layers. Pipeline balance is set to balance here. Okay, so let's see how it's used here. Yeah, let's quickly understand how it is used. Let's put a breakpoint here. And then let's run this. Wait, did we stop this? Let's go. Train. Run. Okay, so it's not even hitting the... Okay, this is definitely not working, as it's not even hitting the required code. So two main set of tasks here. One is figure out how we can reduce the GPU consumption and increase the batch size and just shard the model across two devices I have, so we can train it in a better way. And the second one is, why not do SacreBlue eval on Flores 200 during the training itself, or just sample text. So that's kind of the second set of tasks. Then we have two papers. That's also a third set of tasks, quote unquote tasks. Then we want to play with mine data. That's the fourth one. And then additional curriculum learning is going to be for bigger runs. And then we also need to calculate the number of GPUs and estimate compute hours, and then get the grant and kick off the bigger run. So that's kind of a lot of these questions are about, as you can see, about model parallelism and just how to run this efficiently. Okay, so I guess we have to just step through everything. So I'm gonna go here, call main, start here, run. Oops, run the train. Did I run the correct? So let me just run this one. And let's hit the breakpoint and then start stepping into the code. Okay, so here we are. Okay, so if it's model parallel, then we do what? Then we pull pipeline parallel preconfig, see what this does. Balance exists, devices exist, true. If either of those are not correct, if they're false, then we throw exception. Okay, now we grab the balance, it's going to be 12, 12, okay, and then grab the devices, it's going to be 0, 1, okay, and then the length is the number of pipeline, that's 2, that looks good. And then here we have 2, so if this is bigger or equal, and this is 0, then it's good. Okay, and then final number of pipelines per node is going to be 1. Why? Oh, okay, they're assuming now we're running this across the nodes, but we in reality just want to run this on a single node because we can't get the model or parameter sharding to work on a single node. GPUs per node. Okay, this is an error, but let's continue. Okay, and then we do what here? We assert that this is smaller or equal to the number of devices we have in the system. We create testing. Okay, and then pipeline parallel post in it. Let's go and see what happens here. Assert that this is divisible. And then distributed roll size is going to be 2 divided by 2, 1. GPUs per node, 2, and then save this. Okay. If this is not none, then start a rank. Okay, so we spawn. Okay, so I guess the only difference is we want to have 2 pipelines per device. Okay, let's just go back into here again. Let me rerun train quickly. Let me just try to hack that quickly and see what happens. Let's just quickly hack it. So here, as you saw, once we get to here, we have GPUs per node 2, number of pipeline devices, and then we return 1 here, number of pipelines per node. Let's just put 2 here, directly hard-coded. And let's retrieve. Okay, so now let's put the breakpoint there. We have 2 pipeline devices and we have 2 per node. So if we run this now, just curious what will happen. Let's go. Okay. Where is that one used? I think it's used here. Distributed number of processes. Okay. That's the only place where it's used. Okay, let's exit. And let's just kick it off. So we have 2 devices and both of them are on the same node. That's what I effectively tried to tell it. Yeah, it's just failing. Nah, this is not gonna work, guys. We have to do it properly. It has to be either pipe parameter or model sharding or data parallelism, nothing else. This makes sense when you have multiple nodes. Transformer encoder, embed. Let's see in the train here, pipeline, not even mentioned. Build model for the task. Now let's go here and let's run this again. Okay, hit F5. Let's go to train. Let's enter here. Whoops. Enter here, building the model. We're in the epoch task, okay. And then models building the model. Fairseq. Let's go. Base architecture. Here. Build the model. Transformer based model. Okay, and then we're just, is there any mention of pipeline here? No. Let's just exit. Oops, let's just exit here. Okay, let's exit here as well. Exit, exit, exit. Enter the rep. What happens here? And then the wrap. Whoops. Okay. Fully sharded. Initialize. What are the arguments? And what are the keyword arguments? This is just the transformer model. And then we have the keyword arguments, which are process group, reshard after true, flatten, false, cap. There is no mention of pipeline parallelism at all. Okay, let's just see pipeline. Why do we never hit model parallel? Why do we never hit this one? Where is this one called? Here. And then return it. Okay, so we probably have to, no, I mean, okay. I definitely give up on pipeline parallelism because that won't be the way that we are using it. I just wanted to quickly hack it and see whether it works. But apparently it does not. At least not out of the box without me trying to spend a ton of time fixing their issues. We just fix this here. Okay. Go back here. Remove this. Okay, this is all good. Return back the memory efficient one. Just put it here with a comma. Revert them back to 12, we did. And revert this validate 2000, we did. And then checkpoint activation, try this and see how it affects, and remove the CPU offload. Okay, so we tried a ton of different options. None of them really worked, guys. None of them really worked. So yeah, I guess one thing we can do is I'd love to run this and just understand where is this reshard after forward. Where is this one called? Where is this one actually used? Let's just try and find the Python files. So it's specified here, and then the fstp config happens here. Where do we actually use it? Okay, let's go run this train, enter inside of the train, find the train step, and just enter there, and then just put a breakpoint somewhere here when we start doing the forward and backward pass. So just stop here. So I'm gonna basically run this and wait until we hit that line. At the same time, let's quickly follow what's going on here by watching the GPU consumption, the VRAM usage. Quickly check my mobile. I have to see some notifications here privately. Okay. Let's go fully sharded data parallel. Enable the wrap with the configs. What's the config? We reshard after forward should be true. So let's see. Reshard after forward is true. There is some process group. Mix precision is set to false. Reduce scatter is set to false. That's the FP32. Flatten is set to true. CPU offload false. Compute D type is float 16. I think we support bfloat, so we could go with bfloat. Is mixture of experts? No, it's not. State dictionary device currently on CPU. Okay, so we pass all of that. Use sharded state, wrapper class. Where is this? Inside of main, and then enter, and then self generator, and we are here. Okay, let's just try and step into this. Whoops, not here. Okay. Enter. Step into this. Again, not here. Enter. Ton of ugly code. Just a ton of ugly code. completely. I literally didn't understand anything that happened there. Fun. Build model. Okay, let's just hit F5. Let's wait until we hit our forward pass. And before we go there, unfortunately, I have to stop this again. Unless I wish for my stream to crash, I have to reduce the number of layers here to 6 and 6 quickly, and just add a to-do to myself. Return back to 12 layers. Stop there. And rerun. Let's go now. Run. Okay. Hit the 5. Hit the 5. Waiting to hit the actual training step line. I swear to God, I'm gonna understand every single detail of this code. Let's go. Let's go. Train step. Enter here. Just step into this. Okay, train. We're inside of the fairseq task, train step. And then we go here. This is the forward step. Enter. This is the forward step. So here is where the magic happens. So somehow, let me put the breakpoint there. We somehow, excuse me, have to understand whether this is doing some resharding of the parameters. So if we step into this, go here, enter, lazy init. So we are now in the forward pass of the fully sharded data parallel inside of fair-scale. So we are directly, let's see what lazy does. Lazy initialization. That should happen lazily, typically right before the first forward pass. So we now go through the parameters, and that list is, let's see how long, 1. So we enter here, we grab the parameters, and that's just gonna be, shape of that is what? Oh my God. Okay, so that's the flat. Those are the flat parameters, and we see how many we have. We have 219. I think this might be like, I think this is encoder. And then we also have decoder, which is additional 200 something. And then we have the embedding table, which is also around 200. That makes it 615 million in total. So let's see what this does. So we have a flat self-params, which is flat. Now in this FSDP wrapper class, we keep a list of to be flattened and not to be flattened params for doing sharding, gradient hooks, etc. Note that the ordering of the list matters. Flattened params are always in the front. The self number of flattened params are computed and kept here to support summon full params and shard to full weight consolidation. Okay, let's go back to where we are. Initialize parameter distrib. What was the name of that one again? Init param attributes. Okay, so we enter here. I always wonder, like, we now go here. Why do we? Okay, here it is. Why do we always enter weird places when I hit F1, F11? Okay, here we are. Assert that this has attribute is sharded. Okay, then we grab the data. Here it is. So what's then the type? What's the type of P if we extract the data from it? Type of P is the flat parameter, some fair scale class. Original size. So what's going to be the original size? Okay. Let's go. Use FP32 shard if you're not in using mixed precision or offloading params and graphs to CPU. If this is sharded, then we grab number of elements times the world size compute device and compute type. And then we free the storage for this guy. So what's the what's going to be the size now? P full param padded shape. Okay, so that's the original size actually. Huh. So it might be this is the size of encoder and decoder. Okay, let's see. And then we exit by setting the, okay. That's it. Initialize is root and setup streams. These steps would ideally happen in init, but is root can only be determined after the entire model hierarchy is set up. Thus we run it lazily. Let's enter here. Completely I'm clueless what's going on. Let's see. If final backward callback is never been queued, state should be idle. set up the streams. Who is available. Stream to move main FP32 params to FP16 for forward. So one CUDA stream. Stream for all gathering the parameters. Stream for overlapping grad reduction with the backward. Reduce scatter bucketer 25 megabytes. And exit from here. Okay, set up the streams. Set up the output hook. Let's see whether this ever happens. Nope. If it's root. Cast buffers. Buffers stay on GPU. Buffers stay on GPU. And don't get sharded. Since cast buffer is applied recursively, we only call this from the root instance. Let's see. Okay. How long is this list? We have no idea because it's a generator. Add the module. Let's see whether we ever hit this or this. Buffer to device or compute device. What's buffer? Okay. Okay, cast buffers. Reshard after forward. Disable shard on root. Don't free the full params for the outermost root instance. So this one will not get resharded. Okay, so that might describe the discrepancy between the number of parameters on two GPUs. Nah, this is something you have to literally be doing for days to understand the details. All gather, wait the stream. Grab the current stream and wait for it. And then that's it. That's the init. Training set forward. All gathered full params. This will also transfer FP32 to compute D type, which is going to be FP16. And then register post, and then we do the forward for the module. Okay, let's go here. Let's see where we are. We are inside of rebuild full. With the all gather stream. Okay. If mix precision or move. Okay. If move. Okay, otherwise, if it's sharded, otherwise we do what? Okay, grab the data. If move parent recipient full force, full precision, we need to cast to CUDA for the old getter. Non-blocking, and this is CUDA. So move to CUDA in a non-blocking fashion. And then the data is actually what the data is going to be. All of these 200 something parameters. Get the size. And assert that this is modulo world size 0. Okay, let's go and allocate the storage. Okay, and then we'll get our base, the output tensor, which is again what? And then free okay. What's going on? Huh. Illegal memory access. Okay, that was because that's because I was trying to step through and I didn't progress the second one. Not clear. Okay. Let's try and rerun it quickly once more and stop. Before progressing, we have to push the second process to advance as well. So this interaction with debugger and multiple processes is weird, but at least we have a debugger. Changes things quite dramatically, in my experience. Okay. Let's hit F5. Again. Here we are. Enter here. Go here. Enter. Exit here as well. Exit. Exit. Whoops, let's just remove all of these breakpoints. Let's remove all this. Forward. And then let's progress the second one. Where is the second thread? Run. Enter. Run. Enter. Just step over. Let's go. Rebuild the full. Let's advance the second one. And then if we shard, then we free the full params. This one is false, but the previous one is also false. Why? Why are both of them set to false? I have no idea, but that's basically the reason. And then done with forward, we are now in the idle state, and clear. So why don't we ever enter here? What's the thing? Okay, let's put it here. Let's put a breakpoint here, and let's put a breakpoint here. How many times do we get to this point? So we are basically not resharding. So that means we basically materialize both both models on both GPUs to full number of parameters, and that's why we're not seeing any sharding benefits. Let's see, why is that happening? Okay, let's see. Reshard set to true for one of these two. Okay, for both of them, it's gonna be set to true. So for this one as well as for this one, both of them are true. Okay, hit F5, hit F5. Okay. Reset. Hit F5. Hit F5. Okay, let's go. Let's go. Let's go here. Enter. Okay, so this one is going here, but the other one is still here. Wait. Oh, okay. So when they say root, they basically mean what? They mean like this whole node or what? Why would this be set? Huh. So both of these are basically being set to false. Disable. Why is this set to true here? Where is this set? Disable the shard on root. Why would one set that? Disable. Optional. If true, will be set to false. Root module to improve performance. Okay, let's try. Let's try and set this to true. To false. Disable. Don't disable. Don't disable it, and let's rerun. Again, we are here where? We are inside of fairseq. Rerun train. I'm not sure what they refer to as a root module. Probably this wrapping does this recursively. Let's see what is going to happen. Okay, this is going to be set to disable, false, don't disable. Okay, don't disable. Let's go. We're gonna now hit the forward pass. Okay, go. Proceed. Let's grab the second one. Huh. Nothing really happened. We're still at 23 here. But no matter what I do, I'm not managing to save any VRAM there. This is a bit lower. We have to understand this concept of a root in FSDP. Let's see what this FSDP root does. Let me just once more quickly enter here and see whether this model is actually the full transformer model, or are they sending, are they maybe some submodule of the actual transformer encoder decoder model. And then we need to understand this wrapping with FSDP, like how can we okay, we can move this now. I'm going to set this back to true. Let's remove this. Let's go. Let's wait until we hit this. Okay, the model is fully sharded data parallel with this buffer size. Inside the train step. And this one was sent in here. Here, self model. Whoops. Self model is what? Okay, because we're inside of trainer. Okay, that's the self model. Okay, and then in the top level function here, build model. We build the model. And then we have the model here. And then we pass it to the trainer, I think somewhere down the line. Yeah, so we just pass it to the trainer. And so the trainer just takes the model and just allocates it, assigns it to this underscore model variable. Okay. So this should be just a whole complete model. Yeah, definitely looks like that's the case. Okay. Stop this. Go to train. Go to FSDP wrap. So we really need to understand this. what is going on here? Wrap the layers modules in FSDP. This falls back to a no op if fairseq is not available. So wrap. Okay, let's go here. Let's enter the FSTP wrap, and then we're inside of this context. So let's see how this is going to play out. So once we build the model, maybe we can just put the breakpoint here as well. Ignore the context for the time being and just wait. Okay, enter inside of the build model. Okay, and then we can just exit immediately. And now we enter the FSTP wrap. FSTP wrap. No, I said go outside. Okay, here we are. Let's go. Sum the number of elements of the module. $12 million. Because of that, we return back the module. Okay. Build encoder layer. Let's go. And then add the module. We go further. We build the next one. And then the number of parameters again 12. So we go to the next one. And here again. And again. And again, I guess it's gonna happen like 12 times because we have 12 layers. No, this one is now bigger. This is now 16. Let's see what that gives us. So that's a decoder layer. Let's go. Again, decoder layer. Actually, it will happen 6 times because I reduced the number. Let's go. Again, 16. So in general, if we have like calculator, if we have like 16 there, let's say 17 times 12, that's 204 there. And then for this, for the previous one, we had like, okay, so that adds up. Let's go. Let's go. Let's go again. Let's go again. 12. Now we're in the second. I think this is the second process. So this is again the encoder layer. Let's go. Let's go. Again. 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 Almost done with the, oops, this is now decoder. Second, third, fourth, fifth, sixth. We should exit the loop now, I think. Yes. And then let's see, do we hit wrap again? We do. This time, whoops, no, my God. Why did we go there? If it's not none, otherwise if it's none, then just wrap. Okay, so what's this module? Okay, this is the whole thing, and then we wrap it. And by wrapping it, we do what? We do this fair scale, the whole model. We might be able to. I think I know what we can do, guys. I'm gonna try one thing after this. Whoops. I'm gonna reduce from 100 million to 10 million, and that's gonna trigger this wrapping. Let me just see what this does. Grab the module, which is our transformer, and just what's the wrap overrides? Use sharded state process. Okay, let's just enter here, and then we initialize. This is the init process group, rank, world size, reduce. We save a ton of things here. Let's just step through this. But I have an idea. Checkbox, reduce the trigger number for sharding to 10 million. All layers will get wrapped up. Let's go. Ton of different settings. Buffer size. If flattened, to be flattened are these. Why 257? What happened here? We go through the named and we just append them here. Okay. Flatten. So this is the wrap module. Snap. I should have stopped here. Wait. Rerun. Let's just wait until we hit that line. Super hard code today. Let's go. Okay, wrap. Run. Okay, here we are. Let's enter into this one. A wrapper for transparently flattening a module's parameters. Okay, let's go. What's happening here? We go through these, flatten the set, and then flat parameter, and we pass in these parameters and requires grad. What does this do? Flat parameter, fair scale, just bunch of okay, and then we go through the parameters. If it's instance of a parameter, then we reshape and concatenate. Okay. And then we pass in the data up there. Got it. So this one keeps the flat set of parameters. Flatten, register, exit from here. Okay, let's go. Shard the model parameters in place. Will this reduce anything? Shard. Okay, that's it. Now we exit here and we are done. So this one basically wraps it up, but I'm not sure what this one does. We go with this, and then we go inside of it with, there's two context managers here. Enable rep with a config. Okay. Before we go any further, let's go and minimum num parameters to rep, reduce this by 1, 0. Again, to do to this number, but now we want to reduce this. So 10, 1, 1, 2, 3, 1, 2, 3, 10. Let's see how this goes. Again, let's put this here and see how often we are going to be wrapping here. Remove this, run. Last shot, and then we're going to make a small break, couple of minutes, and we continue until 4 something. I think we have 1 more hour of streaming. Let's go. Number of parameters, this, and we wrap it immediately. We wrap it immediately. That's it. That's what I was trying to do. So let's now see when we hit F5 and F5 here. Just go. Just go. Let's see what happens. Let me see whether we save some memory now. Okay, I hear some running. Okay. There is maybe some slight improvement, but still not significant. 22 to 16. Let's see whether this keeps like this. Oh, but this is the improvement because, wait. Yeah, this is because we are running obviously with only 6 layers. If we went back to 12 layers, I don't think anything really changed. So like, we rerun it like this. Let's see. Let's see how this goes. I doubt anything will change, just given what we saw with 6 layers. Let it run. Okay. 18. This seems to be better, guys. This seems to be better. It's 18. This is good result. Okay, this is really, really good result. Let me try and push now the number of tokens. This is a great result. Nice. Wait. This is amazing. This is amazing. Let's go. I think we figured it out. So let's now just try and max tokens. Let's push the max tokens to some crazy number. When I say crazy, I mean 5,000 tokens. Let's run this. It might be doing parameter sharding right now. Huh, interesting. Let's go. Let's see. Let's see what happens. If I manage to figure it out just by setting this single parameter, that's amazing. So it means it's already doing parameter sharding by design if you set the right threshold. And then we don't have to care about Megatron, we don't have to care about pipeline parallelism if this works. But it does not because recovering from OOMs. Let's see whether we can at least increase it a bit. Like, can we go to 3,500? Would this work? Yeah, this is underwhelming after all. I expected at least being able to double the number of parameters. But apparently not. Let's go. Will this work? On the very edge. On the very edge. We are on the very edge. 24 here. Let's see. Nah. Failing. After a while it fails. After a while it just fails. So there's no way we can go past this without entering the unsafe zone. Okay, guys. Now, a couple of minutes of a break just I need to reply to some messages. Let's say 5-minute break. Be right back. So that means now it's 3:18 p.m. CT started. Okay. just. Mm. Okay, that was definitely a bit slower than I thought. I have a ton of messages I have to reply to, guys. So I'm a bit slower to get back to the stream. The live was even dropping the FPS. Let me see. Am I running anything? No, I don't think it should be failing. Antonio. I guess you were watching maybe some previous moment when I had ran the models and thus the VRAM was kind of squeezed out. Okay. So the conclusion is we did not manage to get this to do the sharding that we wanted. Yeah. Now should be good, right? Awesome. Thanks. Thanks for letting me know. Okay, so reduce the number of sharding to 10 million. All layers will get wrapped up. Yes, but this did not solve it. I guess what we can do now is just submit an issue, and then after that we can go and read the papers just to get some familiarity there and just to chill my brain a bit from this hardcore parallelism debugging stuff. Okay, let's create an issue either on fairseq or let me think. Where do we want to create an issue? I guess in fairseq, actually. But nobody's replying to any of these issues either way. Create a new issue. Maybe more of a question. Okay. So yeah, I know about all of this, but it's not working as we are expecting it to work. Increases the speed for large models. I tried using everything really. So let me kind of copy all of these. And let's go here. We did not find the answer, so I don't know what to do here. Let's see. Module, process group, reshard, disable. Move gradients to CPU, no broadcast. Okay. Mix precision. Okay, let's go back here. We tried a ton of things, including setting this we don't even want to use this one, so I'm going to remove it. Okay. Was it model parallel size? I think it was. Model parallel size. Yes. Okay. There is this root. Let me just go here. Train. FSTP wrap. Actually not there. We need to find the FSTP class. Let me see where it is. Fully sharded in it. Root. Do they mention the root here anywhere? I noticed that the code sets the shard after forward to false for the even with the most pessimistic calculations, one would expect when using Atom that I'd have what, like 12. So we have model parameters, activations, gradients, 24 bytes. Which would give us what, 650 million times 24, 15 gigabytes. Okay. FTP paper is here. So reading the paper and the blogs. I'm expecting that sharding is happening in the background, and thus a reduction. And thus I'm expecting a reduction in my peak memory. Okay. I do see that data parallelism works, so that part is good. Reading FSTP paper and blogs. I'm expecting that parameter sharding is happening in the background, and thus I'm expecting reduction in my peak memory. Okay. What's the name of this parameter? False for the root modules. That by reducing the that did trigger nested wrapping, but did not help. Even with the most pessimistic calculation one would expect. I tried deploying arguments until I managed to reduce my peak consumption. Let's find the installation instructions. Install. Okay. So is it possible to do parameter sharding for smaller models like 650 million parameter encoder-decoder transformers? I do see that the parallelism works as expected. So that part is good. But reading the blog and reading the paper and the blogs, I'm expecting that parameter sharding is happening in the background, and thus I'm expecting a reduction in my peak memory. I noticed that the code sets the I also noticed that the code sets this parameter to false for the root module, so I tried circumventing that by reducing this from 100 million, which is default, to 10 million. That did trigger nested wrapping, nested FSDP wrapping, but did not help. I have two RTX GPUs, and with only 650 million, both of my GPUs are already fully saturated. Even with the most pessimistic calculations one would expect when using Atom, that I'd have roughly 24 bytes per parameter. Atom state has 12 bytes, activation gradients, all full precision, assuming atom state 12B and then activation gradients model parameter. And assuming all full precision. What I'm doing instead is being used almost peak memory, even though I'm using FP16, even though I'm supposedly using frame sharding. Okay. Okay, yet another issue. Let me go back here. Okay. So that's that part. I'm gonna send it to my friend who has some experience with this in GPT-NeoX. Just a second. Okay. What next? We have papers, but I would be reluctant to start this. Maybe we can go. Let's just go and cover these papers. I'm gonna open them up. Let's just open them up. Let's see how many pages. 13 pages here. Effectively like 9, and then here, let's see what happens here. 14. So this is the altimetric, whatever that is, has something to do with visualization of the attention. So we can maybe start with that one. Let me see the chronology. This one came before as well. So let's start with this one. So this one was published in 2020, in May last year. So I guess very much related to Meta's efforts behind the No Language Left Behind. So let me just paste this to Discord and let me tell people that we'll be going through this. Let me send that to general as well. About interpretability. Okay. Let's go through this one quickly. Okay. Towards opening the black box of neural machine translation, source and target interpretations of the transformer. So mostly Meta folks apparently, or not mostly, actually a bunch of people from this university and only a single person from Meta. Yeah, that's my mistake. Okay, so let's skim the abstract. In neural machine translation, each token prediction is conditioned on the source sentence and the target prefix, which has been previously translated at a decoding step. and the target prefix, conditioned on the source sentence and the target prefix. Okay. However, previous work on interpretability in neural machine translation has mainly focused solely on source sentence tokens attributions. Therefore, we lack a full understanding of the influences of every input token, source sentence, and target prefix in the Mahler prediction. In this work, we propose an interpretability method that tracks input tokens attributions for both contexts. Our method, which can be extended to any encoder-decoder transform model, which is very much relevant to us, allows us to better comprehend the inner workings of current NMT systems. We applied the proposed method to both bilingual and multilingual transformers and present insights into their behavior. So here are some charts here. So alt-type plus results for German-English translation example. We obtain source sentence and target prefix to the columns, interpretations for every predicted token row. So German is here, and this is English, source sentence and target prefix interpretations. Okay, damit ist unsere Aussprache über den Stand der Europäischen Union geschlossen. The debate on the state of the European Union is closed. The debate on the state of the European Union is closed. Why do they have, let me just understand this. What's the thing with having translation both here and here? That debate on the state. The debate on the state is closed. Okay, let's see what exactly are they showing us here. And then here is the encoder-decoder architecture. Here we have as a source Spanish to English. And then here the self-attention block left at each position I can be decomposed as a summation of transformed input vectors right. The closest vector, T2 of x2, contributes the most to x2 hat or tilde. Okay, I guess this is just the explanation of how attention works. So you get the value vectors, you then sum them up, and potentially some noise, I guess, the dropout modeling or whatnot. Self-attention and cross-attention modules in a decoder layer together with its contribution matrices. In green, it's showing the information coming from the encoder, and in red, the information from the decoder. Highlighted is shown contributions at a single step, time step t. Okay, so what is this? Is this like the cross-attention part? Yeah, this is the cross-attention. So we also take into account encoder activations. We attend to them. Confusing drawing. Source. S stands for source, and then C stands for what, and S stands for what. Not clear what this picture is telling us yet. Let's see what else. Okay, so this is just encoder does have full attention pattern, whereas here we have causal. So this token here attends all of the previous ones. The previous token attends to itself and the previous ones, as well as all of the encoder tokens. Okay. Source input attribution. Just quickly skimming the paper just to get some high-level overview, and then we can go into the detail. I love, me gusta. Okay, so this is encoder. and then we use that to condition the decoder. Why are they now using this weird multi-layer perceptron type of visualization? And then there is some algorithm there, contributions, correlation between attention weights given the EOS token, denoted like this, end of sentence. Source, multilingual model, Espanol, Spanish to English. Conclusion, we propose ALTI plus, an interpretability method for the encoder-decoder transformer that provides token influences to the model predictions for the two input contexts, source sentence and target prefix. Hello, Smith. Welcome, man. By applying ALTI plus to a bilingual and a multilingual NMT model, we're able to discover insights into the behavior of these black box models. Unlike previous methods, we can now observe dependencies between tokens in the predicted sentence and quantify the total contribution of each of the contexts. Okay. This allows a deeper exploration of current NMT models. Our findings include the role of the source EOS token as a mean to avoid incorporating source information, the absence of source contribution when producing hallucinations. Interesting. So they probably leverage this information here for the next paper. This is how they catch the potential hallucinations. The absence of source contribution when producing hallucinations, and the lack of source contributions when translating from English to a low resource language. Again, basically meaning the model consistently hallucinates using just the decoder knowledge for the low resource language. So ALTI plus overcomes the limitations of previous interpretability methods, and we believe it can help researchers and practitioners to better understand. Okay, limitations, it is able to measure the amount of contextual information in each layer representation of the transformer. We use the influences of each input token to the last layer representation for evaluating input attributions for the model prediction. However, our method does not consider the softmax layer on top of the transformer. Therefore, ALTI plus does not provide explanations for each of the output classes, target vocab, as opposed to gradient-based methods. Ethical considerations, really? Okay. Anything else in the appendix that might be interesting? Layer normalization. Okay, nothing interesting there. Full derivation. English to Zulu. Norm of the value vector from encoder outputs in the cross-attention of the alignment layer. We provide mean and standard deviation for each head in the bilingual model. Similar patterns are observed across layers. Okay, so what's this? Head. The value of the EOS is very low, and then final punctuation or whatnot, big variance, and then there is the rest of tokens here, higher norm values. Okay. Just some examples here, and that's it. Okay. So let's see what exactly they do. What's the insight other than just like visualizing the attention? So transformers have become the state-of-the-art architectures, blah, blah, blah. Attempts to interpret predictions. A large number of works in this line have investigated the capabilities of the cross-attention to perform source-target alignment compared with human annotations. A large number of works in this line have investigated the capabilities of the cross-attention to perform source-target alignment. Okay. Compared with human annotations. Gradient-based and occlusion-based methods have also been evaluated against human word alignment. The former computes gradients with respect to the input token embeddings to measure how much a change in the input changes the output. The latter generates input attributions by measuring the change in the predicted probability after deleting specific tokens. However, there is a tension between finding a faithful explanation and observing human-like alignments, since one does not imply the other. Okay. The decoding process of an NMT system consists of generating tokens in the target vocab based on the information provided by the source sequence and the previously generated tokens. Target prefix. That's what they call the target prefix. However, most of the work on interpretability of NMT only analyzes source. Recently, these guys proposed using layer relevance propagation to analyze the source and target to the model prediction, and later analyze its behavior during training. Nonetheless, they apply their method to obtain global explanations as an average over the entire dataset, not to get input attributions of a single prediction. Gradient-based methods have been extended to the target prefix, although they do not quantify the relative contribution of source and target inputs. Concurrently, encoder-based transformers such as BERT and Roberta have been analyzed with attention rollout, which models the information flow in the model with a directed acyclic graph, where nodes are token representations and net is attention weights. Okay. Okay, I guess that's this visualization we've seen here. Tokens and then attention weights. Got it. So this is just some interesting way of representing transformer, I guess. In the computer vision literature, combine this method with gradient information. Recently, these guys have presented ALTI, aggregation of layer-wise token attributions, which applies the attention rollout method by substituting attention weights with refined token-to-token interactions. In this work, we present the first application of a rollout-based method to sequence-to-sequence transformers. Our key contributions are: we propose a method that measures the contributions of each input token, source, and target. We show how contextual information is mixed across the encoder of NMT models, with the model keeping up to 47% of token identity. We evaluate the role of residual connections in the cross-attention and show that attention to uninformative source tokens, EOS, and final punctuation mark is used to let information flow from the target prefix. Interesting. We evaluate the role of residual connections in the cross-attention and show that attention to uninformative source token is used to let information flow from the target prefix. Got it? We analyze the role of both input contexts in low and high resource scenarios and show the model behavior under hallucinations. Background. To understand our proposed method by briefly explaining the transformer in the context of NMT and the aggregation, the ALTI method. So that's the original method they built upon, because this is, I guess, ALTI plus or something, how they call it. Okay. So encoder-decoder transformer, we can probably skim that. They show it in figure 2. Is there any mention of figure 1? Interesting. I love when they show a figure without even referring to it. We obtain source. Got it. So here, this tells us what? Debate. I'm not sure how to interpret this plot yet. We'll see. Okay. So let's go here. So they just give some context. This presents the prefix. with xj being equal to y0 used as a special token to mark the beginning and end. Okay, multi-head attention. Sequence of token representations of dimension D entering layer L. And this is the output layer representation. Each of the H heads. Basically, we do the summation of value vectors in each of the heads. And we sum them up across J. So J stands for the context length. The output of MHE. Just looking at the terminology more than anything else. Just what symbols are they using? This is equivalent to sum or heads. Got it. So this is the final thing. So they get ZHs, the output of MHE for the ith token is concatenating each ZI, which is basically the output here. So we concatenate them and then we map them. Okay. Layer normalization applied over the sum of the residual vector xi and the output of the multi-head attention. Okay, so you grab the output of this and then residual connection, and then we apply. So this is the post layer normalization layer. Merging them, we get something like this. And considering that this is the case, we can formulate the previous equation as this. Okay. So this is a skip connection. This is the mapping and bias. Okay. Aggregation of layer bias token to token interactions. Okay, so this is the ALTI method. That's that part of the background that we care about. The layer normalization operation over a sum of vectors ln, and then the sum of vectors as in equation 5 can be reformulated as, and then this form where this maps from D to D dimensional space. This allows us to express equation 5 as an interpretable expression of the layer input representations. Okay, so the output is basically looks like this. This is the bias term, and TI transforms the layer input vectors. Okay. With the residual connection, xi only considered in the transformed vector. These guys propose to use Manhattan distance between the output vector and the transformed vector as a measure of the impact of xj on xi hat. Okay. By taking minus this distance, larger distances reflect lower, more negative influence. Okay. Then distances are normalized to obtain the contribution of token representation j to token representation I, like this. Okay. So what's the size of this one minus this over some sum? I guess that's this image here. Let's see what they do here. So they compute. So this is contribution of xj token to xi on the output. So how much was that final value of the xi token determined by the value of the xj. And then they do that by, okay, whatever is the magnitude of xi, then we subtract away the distance between them, and then we normalize that over the sum of all of the tokens and their contributions. Okay. Okay, so what's the, if this one is super close, this will be very small, this will be big, and then over something. Got it. So then the bigger this value, the more this token contributes. That's how they manage to capture the notion there. So given the matrix of layer-wise contributions, where each row contains the contribution or influence of each xj in xi tilde. Okay, Alti method follows the transformers modeling approach proposed by these guys, where the information flow in the model is simplified as a direct acyclic graph, where nodes are token representations, and edges represent the influence of each input layer token xj in the output xi tilde. Alti proposes using token contribution C instead of raw attention weights alpha. The amount of information flowing from one node to another in different layers is computed by summing over the different paths connecting both nodes, where each path is the result of the multiplication of every edge in the path. This is computed by the matrix multiplication of the layer-wise contributions, giving the full encoder contribution matrix. Interesting. So this is how you get the contributions for the later layers. You just keep on multiplying matrices. The amount of information flowing from one node to another in different layers is computed by summing over the different paths connecting both nodes, where each path is the result of the multiplication of every edge in the path. We refer to this as contributions in the last layer of the encoder, where output vectors are E. Okay, and that's the end of this. And here is a visualization again. They unfortunately do not visualize where t of x is here on the chart, but I suppose it's after. Okay, actually it's after this black box here. So I guess that's just, let me think. Those are just value vectors then, looking at this. So this is kind of the attention, probably this is the value vector. And we end up with this, and they're looking at how close are these to x2 tilde, which is the output. Can be decomposed as a summation of transformed input vectors. The closest vector contributes the most to x2 tilde. That's kind of their assumption. Okay. And then they do the same thing just for encoder decoder, which is alti plus. So let's skim through this. Actually, it's 4:20, guys. Let me just think. I will have to drop, and my battery is about to die either way. So we can continue from chapter 3 onwards to understand what's alti plus. We got some background on the alti, how they do it. So it's fairly reasonable logic. That this part here is a bit confusing, but I think it basically boils down to being just a value vector It's just a value vector that you have to then multiply with the attention coefficient to get the final result. Then epsilon, I'm not sure whether they just model and where they're just modeling here there's some noise or whatnot, dropout or whatnot. Okay guys, catch you after the break. So I actually have some meetings I have to attend, so I'll let you know in the channel when the next stream starts if you're curious to catch up. Follow the channel. Again, here is the open NLLB channel in my Discord. You can find it here and you'll be able to track everything here. Cheers guys, see you a bit later.